business. We're going to start right on time today. Get this out of the way. All right. So today is our last new material day. What I'm about to go, I know, right? Celebrate. Everything I go over today is not on exam 4. So I'm going to start with that just really quickly. This is already in your email. It's obviously on Blackboard that I'm looking at right now. But just to kind of make sure there's like a hard line, like, okay, this is what exam 4 is. Boom. Here I go. All right. So exam 4 is this Wednesday. What's topics? So exponential functions, those are like a, b to the x from our lecture notes, from the practice. There's exponential growth, there's exponential decay. Recognize their domains, their range, and their asymptotes. Compound interest, that was a lesson that was recorded and you watched on your own. You don't have to memorize the formula, like A equals P parenthesis 1 plus all that jazz, that would be given to you, but just be able to apply it. Things you would need to know is something is semi-annually or quarterly. That means N is a certain number value. You should apply some common sense, but I went over that in that video. And then logarithms, so that's pretty recent. Be able to convert from log to exponential, exponential to log. Maybe evaluate a couple without a calculator. I might just have like a short 1 page. I don't know yet. I'm not saying, but if I put it on there so it's a potential, like a short, hey, what are these values without a calculator? Nothing that would be like crazy hard. But do remember, like, for instance, the base 4 logarithm of 1/4 makes us think a little bit. You should be thinking -1 or like ln e squared. So you can use some properties to be able to bring down the 2 and do different things. And also like rational exponents. So if there was like a square root or a cube root, you want to first convert it into a 1/2 or 1/3 exponent form, but something like that without a calculator. So review that. The big 3 properties for property of exponents, properties of logarithms, which the first 2 basically allow us to expand or condense. And then the third one just says bring down the exponent or bring up that multiplier. We use that to solve both exponential and log equations. That was our last lecture. The most recent homework, which if you complete it on time, would be due right now. And an application that used like more compounding interest. Again, I would give you all formulas there, or finding like a half-life. So definitely at least 1, maybe 2 applications in total there. So it feels like shorter topics to me, but there's still a lot involved in all of those. So make sure you're just prepared. Once you finish, there's no lecture afterwards, okay? So you can take off, won't be anything to go. And that's it. That's the end of exam 4. So we good? Everyone knows where to find this stuff? What's up?
Is there a class next Monday as well?
There is. So Monday, April 21st, that's today. All right, so yes, next Monday there is too. Monday, April 21st today. So we're gonna discuss final topic. That should say topics. So it's really kind of 2 things. And they don't like necessarily go hand in hand. It's something that I cut out earlier. It's all good. And something that, well, whatever. So I'll just get through it. So I said rational functions, but there's one other thing too. So we'll get through it and that's it. They are fair game for the final exam, right? So I say that right here too. So what I'm about to go over in terms of lecture is not on exam 4, but will be embedded along with other review stuff on the final exam. So you still need to know it. And the homework's already live on this. Speaking of homework, and everything now is due for full credit next Monday in there. But the hard deadline usually is the following Sunday, but because the final exam, is the next Wednesday, the hard deadline, so for full credit, this homework is due 1 week from today, and then you get 2 extra days for the late day. So May 1st is the hard deadline on all homeworks, just because that's it. We're done. So just keep that in mind. Please get the homework done. So cool. All right. All right. Bless you. Bless you. So this actually is like from section 1.7/1.8, if anyone uses the online e-textbook or something like that. But more importantly, it's called composition and inverse. And I'll make a connection to how it kind of closes out what we've just explored, which was exponentials and logarithms. First, a composition of two functions. I'll say f and g. Informally, so not like mathematically proper, but like just to kind of like, what does it mean? Informally means let's start with the number 5. Could have anything here. And we go into a machine. So 5 is going to go into a machine. We'll keep the machine really simple. We'll call it the doubling machine. Doubling. Doubling. That's not doubling. We'll just do this. The 2x machine. Even easier. So what comes out would be 10. So for instance, one thing we can say, g of 5, since it's the doubling machine, is 2 times 5. We output 10. That's a weird looking one. Basically, that's how a function works. Input, 1 output. Now, we use this 10, this output, as almost like passing off. It's like, all right, I'm going to mold it somehow, and then we're going to pass that output to the next machine. So this 10 becomes the input into a new machine, which I'll just say is the adding 1 machine. We haven't done this, right? We haven't done this? No, right. And so ultimately, 10 plus 1 becomes 11. Because f of 10 would be 11. That's just like its rule right there. But what we've really done is started at 5, applied 1 function's rule, got an output, which became the input to the next function. And that's what a composition is. It's almost like linked machines. Or sometimes, which I'll do right now, explain it like a conveyor belt. Like something comes in, different object comes out, that goes down the conveyor belt, hits another rule, and now a different object comes out altogether. So it's not like we're inputting 5 into both machines. We start here, it gets molded into something, and then that becomes the input into the next machine. And this right here is what a composition of functions is. All right, so more formally, what just took place there would look like this. F, oops, my bad, messing up the colors. So f And this is the operation. It's like a little open white whole circle type thing. So multiplication, sometimes uses a dot. That's not multiplication. It's like an open circle. This means composition. This symbolism means exactly what took place up there. Here's your input. You give it to this function first. It's going to mold it. That output becomes the input for f. And we read this as f of g of 5. So composition kind of translates to of. So f of g of 5. Now, obviously, you're not going to draw pictures every time you need to evaluate a composition. Here's what it does look like. So you keep your outside function, and then you just put this, on the inside. So this is what I call, and what you will call in calculus, the inside function. And that's what you do first. So again, if it was the doubling machine, we'd just say, all right, double 5, that becomes 2. I'm sorry, that becomes 10. And this is your outside function. You do second, which, as simple as I can put, is the add 1, you get 11. I actually like the machine diagram better than the symbols, but once I do a couple examples, you have the machine in your head and you'll see it's not that bad. One thing done, 2 more to go for the entire semester. All right, we're going to just live here for a few minutes. It's not that complicated. Just had to be able to see it. And as I said, there's a major connection to calculus. I won't deviate too much tonight because I want to stick to the track. But in calculus, you'll have something like this, x squared plus 3. So that's a quadratic, but it's going to be inside and out, and this will be your outside function. So you would have to think, you want to see this in calculus as oh, I have a quadratic happening first and then a sign on the outside. And you'll see that in calculus, you'll get there, right? But, and then you do stuff with that. But anyways, I'll let it go. Let's do a new clean example. So we're going to do 2 evaluations. Make sure we really got it. The first function, a little more, stepping it up now. It's not as easy as the doubling or the add one. But the first function is the base 2 logarithm of x, and the second function, or g of x, I should say, is 10 minus x. So this means, well, I'll read it out loud again, f of g of 2, and it means f is the outside function, and g is the inside function. And that's where we start. That's our first rule, right? So g of 2 is 8. And now, evaluate f of 8. What power of 2 makes 8? 3. Done. So our inside function was g. We go to g. We give it 2. 10 minus 2 is 8. So this, again, think of like the machine. We started at 2. 8 is the output. Now f is going to do something with 8. It's going to say, what power of 2 makes 8? 3. Will we get the same answer if we switch the order? Well, we'll find out. G is now the outside function. And f is the inside function. So we go over f. And we'll say f of 2 is the base 2 logarithm of 2, which makes 1. So it's like now we have 1, and g's like, all right, I'm going to use it. 10 minus 1, 9. And so we immediately can see order absolutely matters. There's a question right in the beginning of the homework. It says something like, is f of g of x the same as g of f of x? Nope. Definitely not. Getting the vibe of it? Pretty straightforward. Yeah, okay. All right, so now we'll do it with a variable. And for some reason, some students are like, oh, this gets harder, but it's really not. We're going to follow the exact same thing we've done, which is first put f on the outside and g on the inside. Now, previously, we were able to input a number here and output a number here, but we can't. So all you have to do is replace g of x with its expression. So I'll put that in words. G of x is x minus 6. So we're not putting a number here. Up till now, we've been putting a number here. We're putting an expression there. F of x minus 6.
How do you stop yourself from reading fog
I know.
every time?
Fog and Goff. I'm used to hearing it. I know exactly what the kids are talking about too. That's like saying sin and cost and like Trig World, yeah. All right. All right. So where do we proceed from here? F has this expression. It doesn't have a number, but it has an expression. All we're going to do now is everywhere there's an x, replace it with this new expression, x minus 6. So let me write it, and then you can digest it. So F says, whatever you give me, I'm going to multiply it by 9. So 9, and we're given F, this group. So I'm going to make a note. Use grouping symbols. And then just simplify your answer. Distribute 9. 9x minus 54. And you're done. That's all we can do. We're not inputting a number, so we're not going to output a number. We were given a variable, so we're going to output something that contains a variable. Just makes sense to me. Goff of x. Again, I get it. Some of us will going to have no issue, and some of us will get a little antsy here. First things first, set it up. G on the outside, F on the inside. And if we were given a number, we would make a number. But you say to yourself, okay, I'm just given x. So the only thing I can do is say f of x becomes 9x. So we're going to say, that's all we can write. 9x. So we give it to G. And as I said, use grouping symbols. Even if, well, I'll just do it always. So G says, okay, whatever you give me, I'm going to subtract 6 from it. So we're giving it 9x. And then subtracting 6, right? It's the way I read this. It says, G says, whatever you give me, I'm subtracting 6 from it. 9x minus 6. The only thing that really cleans up here is just get rid of those grouping symbols.
So it's not going to be x squared though. All right, I'm going to repeat that part because I got a little lost. My brain wanted to play 9x squared.
So this says input minus 6. Don't read it as x. Read it as the word input.
Okay.
So input 9x and then minus 6. Similarly over here, this machine says 9 times the input. So if we input x minus 6, we're doing 9 times the input. Does the word input help?
Yeah.
Cool. Good, because I have an example that's going to use an exponent in just a second, so I want to make sure we're good. Right. Those would be your 2 answers for that. So we literally replaced g of x with its expression part. And now I'm going to help Megan out, and it might help you out. So here's, again, how we think about this. Another way of thinking about this. Input minus 1. Input minus 1. And just group everything. Like, so you say the word input, and then when you replace it, you put it in grouping symbols. You'll never get it wrong. So I said input minus 1. I'm going to use a grouping symbol. Input minus 1. So this goes there, and then we're taking 1 from it. Let's clean it up. There's not really much to clean up. Just distribute the 1 in front, and you're done. We'll look at it the other way. So first thing, f of x becomes x minus 1. And now, if you really are following along, we're about to give g, right? So think of the machine. Input squared minus 2 times input. Ooh, I said input twice. So I'm going to need to put 2 grouping symbols, and both of them are going to contain x minus 1. So say that again. We're given g, like think of the machine diagram, this object. So it's going to take it and square it, and ultimately multiply by -2 as well. And then we'll combine it all there. So this is what it looks like. Ready? So input squared minus 2 times your input. Maybe I can do this, do like something like that. Became that. And this became that on that side over there. And then just clean it up. So no one's going to get this wrong because you're going to get minus 2x plus 2. But it's a good time of the year, since we only have a little bit left, to say this is not x squared plus 1. Either make 2 groups and FOIL it out, or know that it's, when you do FOIL it out, you get an x squared. You do get a plus 1, but you're missing a middle term, which is always found by multiplying these two and doubling. You get minus 2x in the middle. So this expands to that. When we distribute the -2, we get that. And we would combine like terms. And we're done. Just further emphasizing too, order matters. You do not get the same answer. Pretty much can guarantee this is the final exam question. This is the level. The first one's a little too easy. It's good practice, but this is where the level of rigor should be. So very good open response question that has 1 or 2 parts to it. You'll practice it in your homework. I have it printed out here, so you'll be able to. Right. Questions on composition? We'll find out. Just to remind you too, this is not on exam 4. I know I said that, some of us walked in late. This is not on Wednesday's test. And we're going to meet next Monday to kind of piggyback off here. So if this does end up being a headache, we could next Monday is like almost like I have some stuff planned, but it's very casual. It's strictly review. All right, 2 more things to do. Again, as I said, this is like section 1617. I'm just putting them together because they play well together.
Very, very top, the first thing you wrote down. What did you write? Like whatever, because I didn't get that.
Where?
At the literally the first thing you wrote.
So we just did composition, boom, and I'm going to hit up inverse. Basically, they're undoing functions. And so I'm going to, again, informally show you what I mean by that. Someone give me a new number. I don't care what it is. 36. And it's going to go into a machine that does something. So a rule will be applied. We could use doubling again. We could use something new. I just want to keep it very general. A rule's going to happen to it. But we're going to compose it with the undoing of this rule. So that's a new machine. You'll see what I mean in a minute. So if this is the doubling rule, this is dividing by 2 rule. Therefore, you would get back exactly what you started with. So it plays really well with composition. First and foremost, an inverse function is an undoing function. It undoes a rule. And it plays super well with composition because, let's keep it mad simple, this is the +1 rule. We would get 37, but then we're going to undo that. So this would be the -1 rule. You'd get back to right what you started with. Ooh, digest all that. But it's there.
Is that an open circle?
Yep, it's a composition. To be clear, how that picture plays well with the formal answer here. We had 36, but it could have been anything. I said, give me a number. It's unknown. And it went into a rule. I wish I did the color differently. It's all good. I'm going to write one more thing here. Both of these are the same. So I'll say, and so I'll follow. Like, we'll talk about it at the end here, but so I can follow the story. So here's our 36. And it went into a rule, F. whatever rule you want that to be. And so you get an output. And then we composed it with G, the undoing of that rule. And so at the end of the day, you get right back what you started with. 36 stays 36. Oops. And now I'll use the top one. These do give the same result. Here's a simple example. Conveyor belt. +1 rule, boom. The undoing of +1 would be the -1 rule. But now let's switch those. Here comes a number. We're going to start with -1. What's going to undo it? +1. So for this, you can switch the order. It's not going to matter. Come up with a new example. ×2. Divide by 2. 8 times 2 is 16. Divide by 2, back to 8. But if you were to switch those, 8 divided by 2 is 4, but then ×2 makes 8. So you can switch the order of that. But the most important thing to recognize is a function composed with its inverse just gets you back to where you started. My bad. What's f of 2? What's f of -4?
1.
And what's f inverse -4? All right, so some answers are being shot. I'm just giving everyone a chance to copy down and then process, making sure we understand what's going on here. I'm going to end up erasing this, but as I'm talking it out. So here's f. Boom. Here it is. And when it's written like this means go to f, input 2. And so we're looking for, what's the output? Well, boom. The answer is -4. This guy. Right, so if you input 2, -4 will come out. We agree? That's how functions work. So this says go to f, input -4. My answer here is 1. But what's f inverse of -4? this is F, which it is. We don't have a table of values for F inverse, but I claim we don't need it. Here's the undoing of F. This is the undoing of it. So what does it have to give us back? 2. Did I really need to draw that second thing? No. I'm going to summarize it in a minute, but I wanted us to kind of really put our brain there. D, E, G. Here it is. This means 6 is going in. That's our input. That's our X. So we just have to give the Y coordinate. See if I can get this all in at once. It's going to be a little too small. What's your G of 6? 2. Boom. You just give the Y. G again. This time we'll give it -2. So we look, that's the input. What's the output going to be? There we go. What's the answer for G inverse of -2? 1. And we're going to summarize it. You might have already be doing it in your head without knowing you're doing it. But the long answer is, well, I said it's another machine. We don't even know what the rule is, but this is going to undo it, which means we're just going to switch it back. We're just, no matter what, it has to give us back to, oh, my bad. I'm messing this up. Let me clean this up. So it's saying, yo, here's the inverse. We're feeding it -2. So these have to be in agreement. This has to be in agreement. So basically, this just means what X has an output of -2? 1. Now that machine diagram would go very well, right? So if this is G, it would have to be 1. Then -2 would go into the inverse. We'd have to give it back 1. This machine, that's the only way this works. And so that I can emphasize it clearly now, I didn't do it as well in the first example. What really takes place with an inverse? The X columns become the, well, I'll say it this way. All right, trying to color code that all there for you. Here's a function. Here's the input. That's where we start in a machine. Boom. And if this is the undoing of that, this has to be an agreement. You start here, you do something, but you undo it, you end it, same thing, right? That's making sense. Now, this is the input of the function in, out, in, out. This is the output of the inverse. I know it's really wordy, right? The input of a function is the output of its inverse. And the outputs of a function, I'll use y, that's the output, is literally the input of the inverse. These outputs become the inputs. More formally, the domain and range switch. The x's become the y's become the x's. And to overkill that, not trying to, and I'll go back there to let you finish writing. But let's go back to the examples we did here. This is a function. This is the input, 2. That's the output, -4. This is a function. We input -4. That's its output, 1. This is the undoing of it. So this input is really in the outputs of the function. There it is. And you bring back 2. Overkill. Give G 6, that's your output. Give G -2, that's your output. But this is the undoing. So it's like, yo, this came out of a function. We need to bring back the 1. The domain becomes the range becomes the domain. It's just symbolic, but once you get it, it's there. All right. So the last thing that plays right into this conversation is given any function in the world, how do we find its inverse? Four steps. 1, replace f of x with y. All right, so there's 4 steps. Let's do it. Here's a function. How do I find literally what will undo this? Step 1, replace f of x with y. It's literally just change it to y. Step 2, replace y with x and x with y. And just to give this a quick, why do we do that? It's the conversation I just said. The outputs become the inputs become the output. We're swapping x with y's. So this becomes x. That's your y. And I'm going to zoom in on this now. Step 3 is to do algebra to solve for y. So let's start by adding 9 to both sides. And how else can we get y by itself? Well, if that dividing by 8 wasn't there, I know what to do. So let's get rid of dividing by 8 by multiplying by 8. So this would be 8x plus 9 equals 3y plus 6. We'll just do a little distribution. 8x plus 72. And now subtract 6. Eight x, let's see, take 2 away, then 4 away would be 66. And finally, divide by 3. That's the algebra steps. I like steps 1 and 2. You don't have to do much except like just put symbols on paper. My mom, who doesn't know the distributive property, she does if I taught her, and I'm just throwing my mom under the bus because she knows I do this. But my analogy here is anyone can do steps 1 and 2 with no math knowledge. This is the math part, the algebra part. Right? So you just practice your algebra. And then step actually 4 is not really, it's a mom step. You just call this final answer the inverse of the function. I always like to check, if I have like time on a test or something. For instance, someone give me any number. Let's use 2. No, that's not going to be nice. Trying to think of. Let's use, I don't know. This is kind of a gross example. I'll let you guys choose what number you want to do. 3? All right. So if I choose 3, what does f output? Let's see. 9 plus 6. 15. 15 divided by 8 minus 9. Pretty gross, but just really quick. So 15 divided by 8. What is it minus how much? Plus 9 or minus 9? Negative 7.125. So how do I check? Well, now, again, you gave me 3. We have this output negative 7.125. So if I give the inverse negative 7.125, I better get back what? 3, where we started. So let's check. 8 times that number plus 66, then divide by 3. 8 times this number, then add 66 and divide by 3, gets us back to the beginning. Cool. So it actually works. It does what we wanted to do. So where the heck did this topic come from? To be honest, chapter 1. I would have loved to go to it in exam 1, but in all honesty, it still fits nicely here to wrap everything up in one coherent package. And maybe you already know this, but if not, we're going to formally say it in like 10 seconds. All right. If you don't have no idea what the heck I'm talking about, I want the inverse of this function. I want the inverse of this function. What undoes logarithms? Maybe you already know, but we're going to find out formally. And this is a good review. Even though this specifically isn't on the test, you'll see. Step 1, call this y. Step 2, interchange x with y and y with x. And how the heck do we get y by itself? What's the algebra to do here? Yeah, put it in its method 1 or 2 from last lesson, right? So that's why I said this. Here's the connection to unit 4's or exam 4. How do you solve a log equation, right? I want to get this by itself. Method 1, write it in its exponential form, or method 2, fancy word, exponentiate by 7. But I'll put it in its log form. So 7 to the x is y. We're done. The inverse and the mathematical, like if you're just kind of like on robot mode, being like, all right, cool, I can do that, I knew that. But the bigger picture is that exponentials and logarithms undo each other. If you already knew that, cool. But now we can formally say it. So like what undoes addition? Everyone in the world says subtraction. What undoes multiplication? Everyone says division. Those are easy. What undoes square rooting? Squaring. That's a little more high school, college algebra level stuff. And definitely college algebra / pre-cal level. What undoes a logarithm? An exponent, an exponential function. Exponentiating cancels out, right? And that's really good to know for calculus, right? I'm not going to take that any further. Ultimately, it was also an example of just applying the 4 steps one last time. That's 2 out of the 3 things I had to go over tonight. Again, normally that would have fit better in Unit 1, but if we were in Unit 1, we wouldn't be able to do this example. Now we can. Right. Cool. Composition and inverses. Got that off our list. Welcome to our final topic. And again, today's a little bit of a loose end. This would have fit better way before, actually in exam 2 with rational, when we were doing long division and synthetic division, this would have been nice here. So has nothing to do with exponentials and logs, has nothing to do with compositions and inverse. So literally just kind of like a weird potpourri flavor, but it's called rational functions. A major thing in Calc 1. I'm going to tell you the absolute must-knows. We would have spent a little more time with it, but I'm going to tell you, I can't let you into calculus. I wouldn't feel right if I didn't go over what I just did and this last bit. So I'm going to keep it short, sweet, and direct. These are the absolute must-knows. First of all, a rational function is the quotient of two polynomials. Math is a language. It's full of vocabulary. I'm going to remind you, a polynomial means like y equals mx plus b. If it has a linear form, it's a polynomial. Or a quadratic form, so if you see like an x squared, or it could be cubic, or it could be fourth power, okay? But it's a quotient of two polynomials. So just really quick, mx plus b, 3x minus 7 over some quadratic. Hey, there's a quadratic. Let's use the parent quadratic. That's a rational function because it's a polynomial over a polynomial. Here's another rational function, x cubed minus 1 on top of x plus 9. This is a cubic on top of a linear. Okay. This is not rational. I'll use h of x. Sine x over x squared. You will see that in calculus, but it doesn't behave with what I'm about to go over. We can call this a fraction, but it doesn't fit into this family. So the characteristics I'm about to describe are true when it's a polynomial on top of a polynomial. This is not a polynomial. This is the sine wave. One of the must-knows is you'll explore this more in Calc 1, giving you the facts, and that's that. But we've seen asymptotes in this class, vertical and horizontal. Rational functions may have a horizontal asymptote, they might not. 3 cases to know. First, I call it the bottom heavy. And I'm going to put it in words. But this is a bottom heavy. What do I mean bottom heavy? What's the highest power up here? Invisible 1. What's the highest power here? 2. Bottom heavy. 2 is bigger than 1. This is not bottom heavy. This is top heavy because the highest power is in the top. Get it? We'll see some examples. So bottom heavy, which means the biggest exponent is in the denominator. Y = 0 is the horizontal asymptote. You will explore it in calculus, but I'm telling you this is a must-know. It'll be one of the first things you explore. Top heavy. Then there is no horizontal asymptote. Literally none. Top of this set of notes says 3 cases to know. You have the highest exponent on the bottom. The highest exponent could be on the top. What's the third case then? Oh, if they're the same, what if there's a tide? I'm just abbreviating here. Numerator and the denominator. Y equals the ratio of leading coefficients. Is this a rational function? Yes, because you have all powers. That's it. There's no funky business. By the way, just remind you, you can't have negative exponents. You can't have like absolute value. You can't have trigonometry. You can't have exponentials. You can't have logs, all right? So it's basically just like x's to whole number powers. No square roots, nothing funky. Yes, all right, cool. Where's the highest exponent? Bottom. Bottom heavy, you just need to learn, right? But the way I think about it is like the bottom, the base level is 0. I don't know how else, that's just how I, done. You write y = 0 is your horizontal asymptote. This is a rational function. The highest power is 2 in both the numerator and the denominator. It's like a quadratic on top of a quadratic. So the horizontal asymptote is a ratio of the leading coefficients, 3/6. That's all. Which we simplify. One half. And for the super mathy people who are like just dying to be like, all right, I want to see it, go to Desmos on your own time. It'll take a second. Type that in, and you'll see in the long run, the graph is approaching the x-axis. That's that. You'll see some funky looking graphs in the middle, but in the long run, on both ends, the values are getting closer and closer to 1/2. And a quick calculus will do this better, but I'm going to tell you anyways. You know, like, let's just think about a number, a big number. So, like 100. The top of this fraction would be 100 cubed plus 6 times 100 squared minus 8. You might say that's a pretty big number. 100 cubed is in the 10,000s, 1, 2, 3, 4, 5, 6. So you're talking about something in the 10,000s. Even just a quick estimate. I don't know, we could figure out exactly what it is. But what about 100 to the 5th power? That's a number with, 10 zeros. That's way bigger. And, okay, so way bigger. Now, why am I bringing about that? If you have something in the 10,000s, but you're dividing it by something in the, I don't know, trillions or quadrillions, that's ultimately a proper fraction, right? Just like 1/2 is a proper fraction. So the bigger you get, this is big, but this is even bigger. And so you're ultimately just going to become 0. Come up with a number, 100, all right? So 100 squared, that's not too bad. That's 1,000. 3,000. And then adding 1, if you have $3,000, adding 1 does change what you have, but you really don't care. Not if you're walking around with $3,000 and someone gives you a buck, you're like, all right, cool, I get whoop-de-doo. You basically have 3,000. And then here, you basically have 6,000. So it's not exactly 3,000 over 6,000, which would be 1/2, but it's pretty freaking close to it because this becomes insignificant. You said it for how many times? 5? You'll discuss that more in calculus, but it turns out it's just the highest powers become the dominant force. Anyhow, when you're top heavy, I'll use the 100 analogy again. 100 squared is 1,000. Taking away 3 is kind of insignificant. So you have about 1,000 over 100. Okay, that simplifies to 100. But you're not approaching anything because if we put in a bigger number, like 1,000,000, it's a really big number divided by a smaller number, but you get a really big number. It's not becoming anything. It's just what we say, nothing. Like, there is no horizontal asymptote there. All right. If I lost you on my little rant, know the 3 cases. Bottom heavy, y equals 0. Top heavy, none. Equal degree or tie, it's a ratio of the leading coefficients. 2 other must-knows. Vertical asymptotes and holds. They play together. First of all, just a visual. This is a vertical asymptote. Not to be confused with what we just talked about, but I'm still going to put it in here anyways. This would be a horizontal asymptote. And this right here is a little break in the graph. We just described how you find this, if it even exists. This is the 3 cases we just went over. So obviously, this is, if it's not at 0 and there is a horizontal asymptote, even though all I do know for sure is that this is a tie. This has to be a tie case because there is a horizontal asymptote, so it's not none, and it's not at 0, so it's not bottom heavy. This has to be the tie case. If you made that connection, cool. That's a higher level question, right? But I'm not even worried about that. I just want to like visualize how you find this. That's what we just went over. We need to find 2 other key things about these rational functions. This thing called a vertical asymptote, and this is a hole. The good news is both vertical asymptotes and holes come from 1, factoring everything, I just got examples left. It looks like a lot of words. Once we get to it, though, you'll see the must-knows are the big 3, and then this, where we're just going to factor and solve very easy equations. And if it's a shared, just going to learn it's a hole in the graph. If it's not shared, it's a vertical asymptote, but they play super well together. All right, so I want to know, first of all, what's the horizontal asymptote? That's actually not the new stuff. Top heavy, bottom heavy, or tie? So it's a ratio of the leading coefficients. 1/1 is done. All right, onwards. Vertical asymptote and holds. So first, we factor everything. Difference of squares is a common factoring thing. And if you're rusty on factoring, as I said, this is a topic on the final exam, but so is factoring in general, right? After you finish exam 4, I said you really don't have any lecture or homework, but if you haven't been studying, and this is like, factoring is always a good thing to review. But if you knew that was a difference of squares, I'd say you're in a good spot. X minus 2, x plus 2. How do we factor the denominator? GCF. There's a common x. So 1, you factor everything. Remember how to factor. Second, says if there is a shared factor. There's not a guarantee. If there isn't, you go on. But there is a shared factor. What does that mean? Right here. Don't cross it out. Just leave it. This is what I mean shared. There's a thing of x minus 2 in both the numerator and denominator. It says in the notes, then find the 0 of that shared factor. So x minus 2 is 0 when x is 2, and that's where you have a hole in the graph. Now carefully pay attention to the third part there. It says, okay, now for all the other factors in the denominator only this guy, this plays no other role. That's the only other factor there. That's your vertical asymptote. And if you were curious, go to Desmos. You'll see a funky-ish graph, not insane, a little funky graph. But on the ends, it's going to be approaching 1, the ends of the graph. And at 0, right on the y-axis, there's going to be a break, a very visible break. And then at x equals 2, take the mouse and cursor over and just drag along the graph, but all of a sudden, you'll see it'll turn. You won't see it unless you do some dragging, but you'll see an open circle, a hole at the graph. And more on that in calculus. There's a couple questions in the homework at the end that say use the 7-part strategy to graph a rational function. I'm not omitting that, okay? I'm going to omit the transformation. So if you're listening, and I'll remind you this again next week, because this isn't due till, I'll remind you this before the exam, I'll say. Right. But I really just want to send you forward into calculus with these must-knows, and that's how to find horizontal and state none, know the 3 cases, and know how to find a vertical or a hole. Right. And you have enough to be successful in calculus. And that is Math 2103. We did it. We covered every objective, all learning outcomes. We're done.